Welcome. Good morning, good afternoon. Thank you for joining us. My name is Matt Schumann, and I'm one of ATA Engineering's business development managers focused specifically within our test group. We're excited to share with you an overview on Siemens Simcenter transfer path analysis, and specifically how you can get ahead of the game by learning how to solve noise and vibration issues before production starts. During this webinar, we will share an overview on transfer path analysis, what the difference between mount and matrix force calculations are, what acoustic quantity Q is, when to use block versus contact forces, and what virtual prototype assembly is. For those who are not familiar with ATA Engineering, we are an employee-owned small business with just under 200 full-time employees. Our staff consisting of highly experienced engineers, project managers, and business development professionals combine decades of industry and academic experience and achievement from undergraduate up to many with PhD level expertise. ATA's roots are deep into aerospace and defense, space exploration, and launch vehicles. We work with companies who provide fun things like themed entertainment rides, and we also support manufacturers of heavy and industrial equipment and automotive and transportation. Our founders began many as aerospace and mechanical engineers, passionate about solving our world's most complex engineering feats. Our professional engineering staff is highly experienced in areas such as structural, modal, and thermal and advanced testing, simulation, and analysis. ATA Engineering has placed offices from the West Coast to the East Coast in strategic R&D locations. We are also proud to serve as a platinum level solution partner for Siemens, going on more than 15 years. ATA has developed our own proprietary software suite to support our customers, and we are one of Siemens' largest software solution integrators for engineering tools such as Simcenter Test, NX, Nastran, Star CCM Plus, Teamcenter, and Solid Edge. We support end-to-end R&D through design, analysis, and test by providing expert training, engineering services, software license renewal, growth licenses, and hardware sales and support. We all take personal ownership in delighting our customers and helping them each to see their success. If you would like to learn more about ATA, our engineering services, and Siemens software and hardware, please visit our website at www.ata-e.com. For today's webinar topic on Simcenter transfer path analysis, I'm pleased to be joined by Peter Scheldenbrand. Pete and I have known each other coming up on a decade and have traveled extensively together in support of our customers' success in test and engineering. Pete is a senior Simcenter test application engineer. He has been with Siemens Digital Industries Software for 30 years and specializes in data acquisition and analysis for noise, vibration, and durability. Pete holds a bachelor's degree in mechanical engineering from the University of Michigan. With that, I'll turn the floor over to Pete. Thank you for joining us, and Pete, the floor is yours.
Thanks, Matt, and maybe you can confirm for me that you see the transfer path screen?
I do.
All right. So I was going to give a little bit of an overview about transfer path analysis today, and some of these, some of the newer things like a blocked force TPA in particular. But first, we'll start with a few things conceptually about transfer paths, just so you understand what it is. You know, when we have a piece of complex machinery and we have people interacting around it, we might have unwanted vibration or noise at some locations surrounding this. So that could be being experienced by a user, you know, the vibration levels are too high, or maybe on a critical piece, the vibration levels are too high, which could cause failure. Could also be a noise issue, you know, maybe it's much too loud for people to be around. And so with transfer path analysis, what we're going to try and do is understand, you know, at a given receiver location or multiple receiver locations where you have this noise and vibration levels, how the noise is getting there or being generated within this system. So we might evaluate things like these mounts, and we'd be able to tell which mount is most responsible. If it's airborne for noise in particular, you know, whether it's coming off of this piece of machinery or this motor versus the transmission, et cetera. So we want to kind of pinpoint and understand where our noise or vibration issues are coming from. When we do this, we typically will characterize the source of our system as a force or as a airborne force called the volume velocity. And then we have our receiver locations, and between where the forces come out of the source and to where we get things as or experiencing things as a receiver, we're going to have things like FRFs to quantify this. So we'd have operational forces here, some sort of FRF that might take a force input, mechanical force input, tells us how much force we get out at steering wheel in this car, for example. Or it might go here, force in structurally, and then comes out acoustic at the operator ear. And it doesn't matter if it's a car or an airplane or a washing machine or whatever the product is, anything with noise or vibration, you can use this technique. And the functions that we use, this FRF could come from test, but it could also come from simulation. It could be a FRF that we simulated for a new vehicle body, for example, in this case. And then we'd want to predict how the existing source will work in that vehicle body. So it can be used in both a troubleshooting method, on current production hardware, or it could be used even in a advanced analysis, trying to predict what the levels are before you actually build the product. Okay, so we got just going to go through some of these concepts, and I'm from Detroit, so this is a car, but again, please understand this could be an airplane, whatever it would happen to be that you might work on. And so we would have in a car, typically a source, like an electric motor these days, or it could be a combustion engine that's attached through mounts to a body structure that goes over to a receiver location like the operator ear. The sound, or when we receive or experience sound at the receiver location, it could start life as an airborne sound, or airborne source. So the term airborne refers to things like if you have this source like an electric motor, and if you have sound that radiates off of the surfaces, that starts life airborne from the source and reaches the operator ear. If we do the opposite here, this would be an example of structure-borne noise where vibration is imparted and forces go into the structure, which vibrate the structure. And then from the structure, from the surfaces here, it goes airborne to the operator ear. And I bring this up just to kind of bring up some of these misconceptions. Structure-borne noise starts life from the source, into a structure, but it does go airborne at some point because otherwise you wouldn't hear it or experience it as noise. So two major categories, I guess, if we're dealing with noise, we have airborne noise and we have structure-borne noise. Now, the same thing with vibration, except instead of going airborne, it would just go through the structure, vibrate this. We would maybe measure vibration at the seat interface, and that would tell us how uncomfortable the vehicle is for the operator. And even that vibration target could be caused by an airborne source. So if this motor was loud enough, it vibrates the structure and then creates unwanted vibration at the operator interface. Yeah. As I go through this presentation, there's a little bit of nomenclature. So capital F will be a force, capital A will be an acceleration, P will be a sound pressure for an acoustic response, and then P over F, if I say that, that means pressure over force transfer function. You could also have an A over F transfer function, acceleration over force, for a vibration target. And if you see a sub O, that means operational. And let me kind of explain that a little bit more here. So here is how we would break down, for like this system with two mounts, where we have a source attached to the structure. F1O means the force at location 1, O means operational. And then we have F2O, that's the force at the second location, also operational. And if it helps, I always try and think when I'm trying to break down a problem to diagnose with transfer path analysis, the dotted orange surrounds the source. And what we're interested in understanding is everything that comes across this orange interface. So in this case, into the structure, we have forces that come out of the source, and we're ignoring airborne, which would also go through the dotted orange. But basically, the point here is it helps when you're going to diagnose a problem. You can make one cut that separates the source from the structure. And as you make that cut, it will designate which paths are available to analyze. So in this case, we have two paths, force 1, force 2. We need the operational forces to characterize the source. And then we would need the FRFs from the attachment locations of the source to the operator ear to characterize the structure. In this case, it's a pressure over force, FRF. Notice it's non-operating. This would be data that if you're doing a measurement that you would take without the vehicle operating. And it's a property of the structure itself, this FRF. And it's a function of force as well. So if I go back, I'm sorry, function of frequency as well. So each frequency you have, this tells you for how much force coming in, how much sound will be generated at the operator ear. So the forces are a function of frequency. So we would want to know how much force is coming in at each of these attachments. And then we would have the FRFs that relate these two attachment locations to the operator ear. And so transfer path, this technique, is really kind of a big multiplying machine. It's going to multiply your forces, whether they're airborne or structure-borne from your source, times some transfer functions to predict what's happening at the receiver location. Okay, so you're going to have P over F1 times F1O, P over F2 times F2O. And again, this is simplified. Normally a mount would have perhaps 3 directions, and there'd be more than 2 mounts typically on a more than 2 mounts on a normal car. Otherwise, I think normally your motor might fall out, which I guess would be a bad thing. So, and this shows the results of a transfer path analysis. I'll show this live in a few seconds, but each bar here represents the amplitude of a particular path contributing to the total. And we have either RPM or frequency down here, and then the different path names. And we can see, like in this case, this body 1Z is one of the bigger contributing paths because it has pretty high levels at a specific frequency. Okay. So P over Fs characterize the structure. Those could be A over Fs if you're doing vibration, and then F1, F2 with the sub-Os characterize the source. Okay. So we're taking these quantities, summing them up to get the total. And we might have a structure that's very sensitive. For a very small amount of force, this FRF generates a lot of sound pressure at the receiver location. So you might look at the FRF and you'd say, this is probably the problem. The structure is too sensitive here at this location 1. But there's a reason why we have both forces and FRFs. If the force coming in at this location was 0, this could be very sensitive, generates tons of sound for very little force. But if the force is 0, it's not going to pass that along and create a problem. Thus, P1 would not be the problem path. The opposite is true too. We could have very high forces, but if the FRF is not sensitive, those forces don't get passed along into the path and thus don't contribute much to the total. So in a way, what we're trying to do is understand if P1 or P2 are the problem path, and there could be 20 or 30 paths potentially on a structure. And by knowing which one's the biggest contributor, we can then look back and see, is it the force or the sensitivity at that location that is causing high levels of vibration or sound in our total. So we really need, you can't go out and measure directly this P1 or P2. We really need the FRF and the force combined together to understand if any given path is a problem. Okay. So let's make this a little more complicated. Maybe we'd have some product like this that has a cab and a motor. And so here's the motor. So we might consider the motor to be the source. So we have our dotted orange line here. And we can see that we have 4 crossings between where we cut the source versus the structure. And there'd be 3 directions each. This is a 12-path transfer path analysis. So we could understand which one of these 4 mounts might be most responsible for what's happening at the operator ear. Now, if you're doing transfer path analysis, or really you break down that source versus the structure. And in some cases, maybe the motor mounts, configuration is all fixed. So that's something you can't change, but maybe the cab mounts could be changed or optimized. In that case, we would define the source to include the frame. And then we would have 5 crossings here, and we'd have a 15-path TPA. Point here is this cut around the source, separating the source and the structure, defines which paths you can address. And you can include what you want in either one. But if you're doing this 15-path TPA versus the 12-path TPA, you're going to have a different set of FRFs and a different set of forces depending on how you define that cut. So hopefully that made sense to everybody. And as I go along, please feel free to enter questions in the chat. We'd be glad to answer them in case I'm confusing people. Going back to a car example, just to kind of give you an idea of how many potential paths here, we'd have things like mounts, engine mounts that separate the source and the structure, considering the engine to be the source. Then we might have airborne off of the engine. We have an intake system that could create sound at the operator ear, tailpipe, and then depending, where you define this source, you could also have things like exhaust hangers, because the exhaust system is attached to this engine in this case. And so you get very quickly a large amount of potential paths, 3 directions each. And these are the types of things that you would need to consider or measure or simulate in order to do a transfer path analysis. So I was using some very simplified examples with those 2 mounts, but you can see it gets pretty complicated right away. Now, maybe over time, you might know that exhaust hangers don't create much noise on the interior. Maybe you'd stop measuring them. But if it's the first time you're trying to troubleshoot something, you probably want to quantify any potential path to understand how much it contributes to the total. Okay. When we sum up all these paths, ideally we should see something like this on the right side here. The sum of the paths should equal, in the case of something where we're able to test it, it should sum up to the total at the operator ear location. So at our receiver locations, we should see a similar amount of vibration from the transfer path and from the actual measurement. If we saw that the sum total wasn't of the transfer path didn't equal the total measured at the actual operator location, we would know that we were missing some paths. So it could be like maybe we considered only structural paths, but there's airborne paths. Or it could be something like we didn't consider that maybe vibration from the motor is getting in through a shock tower and then creating noise. So at least experimentally, you have a chance of figuring out, if you're missing some important paths for diagnosing and troubleshooting an object. Okay. And then we'll talk about this in a bit, but Q is a thing called volume acceleration. That is actually the acoustic force, and we can also have those as part of our total. Okay. So one issue that we have is it might be hard to actually measure the forces coming through the source here. You have to put in a triaxial load cell that doesn't interfere with the dynamics of the regular mounts in order to measure the forces directly. And in fact, people rarely are able to measure these forces directly in many of these applications. So they measure them indirectly. So that means, there's two popular methods. One is mount stiffness, one is matrix inversion. I'll explain these two. With the mount here, we have a rubber isolator, and we typically can measure acceleration with accelerometers easily on both sides of the mount. On the active side, which is A here, and on the passive side, close to the structure. We take the accelerations, change them to displacement, and from Hooke's law from a long time ago, we know F equals Kx, and we get the forces that way. So that means that for each path, if we're going to use this mount method, we're going to have two accelerometers, plus we have to get the mount stiffness values in order to do the measurement. Let me just show that here really quickly. So we got acceleration now on both sides of the mounts, active and passive sides. We have the mount stiffnesses, we have the P over Fs. So that means the force is actually going to be active times minus the passive vibration, which will be done in displacement times the mount stiffness. And all these are functions of frequency times the P over F, right? So we get our operational forces in a different way there. Like with any method, and we'll send out the slides after, there are some things you need to be aware of. Things like if you go to measure the stiffness of the isolator, it's different if you don't take into account the weight of the motor or the source on the rubber. You can imagine compressed rubber probably has a higher stiffness than uncompressed rubber. So you don't want to determine the mount stiffness, when it's not compressed, for example. And then there's things like fixture resonances and other things that we might be careful about as we measure that. Matrix inversion is another way of determining the forces. And this we typically use if the isolator, this mount, or, with the K term here, is if it's not very soft. If it's very stiff, we'll use this matrix inversion. And maybe I can explain why we might do that. So for a stiff connection, you have very little displacement across the mount. So on the active side, maybe I have 10,000.2. On the passive side, I have 10,000.1. And, using a measurement system, maybe I'd measure 10,000 instead of 10,000.1. That's less than 1% different. So very accurate measurement. However, when I subtract these, the active versus the passive, if I use 10,000 versus 10,000.1, the force estimate, ends up being different by a factor of 2, even with this very, very small error in the measurement of the displacement. So the mount method will not work when the active and passive side of a given path have very similar levels. So we have to do something else, and that something else is this matrix method. We will measure local acceleration over force FRFs at the attachment locations. We're already going to be, and then we measure our P over F FRFs to the operator ear location. We measure operational accelerations, and what we get is operational acceleration times, we take this A over F and invert it so that you get F over A. Here's the big inversion. And so then you get operational forces again. Now we have no insight into the mount stiffness or the active side vibration or anything like that. We're only measuring on the passive side. But when we do that, we can get the forces for these stiff connections. Here too, there can be a trade-off or a drawback. If you have something like an FRF like this, an FRF you might have an anti-resonance in that goes close to zero at some frequency. When you invert it, if you take zero and you invert it, you get infinite force, that's pretty high, I think, even for a car. I don't think I typically see my motor come flying out. So we don't want to rely on just the local FRF. What we want to do is measure cross FRFs between all the input locations, and then even add some additional FRFs to condition. And that's why we get this word matrix. We'll use a matrix of FRF measurements times operational accelerations to come up with the forces. And the idea here is that, I don't know if I have a drawing, so I'll draw it manually, is, this FRF here, if I plot it, might, maybe it goes to zero right there, which would cause a problem. But if I have this other FRF and I plot that on here, it might do something like have a peak where the other one goes to zero. And thus the overall condition of this matrix is good, so that I don't get infinite forces because I'm relying on just one of these two measurements to determine the forces. And this is a bad practice over here. Here we have in orange where the sources are attached to the structure. If all these FRFs are close together, they would all have the same anti-resonant frequency, where you could have this infinity condition. So instead, we like to spread this out on multiple parts of the structure, to pick up different resonant frequencies of the different parts to condition the matrix. The software will tell you if you have an ill-conditioned matrix of FRFs. Okay. Here I have the transfer path software. So I started it, and this is from Siemens Simcenter test lab. The transfer path software doesn't acquire data. You would acquire that with signature or impact testing or any of the acquisition modules, but it takes data that you've acquired and kind of assembles it together. So for example, I might have things like a bunch of mount stiffness data. Could maybe take a look. I might have some operational data like forces and things like that. So those would look like here's pound force. It's already been converted to force, or I might have things like accelerations, that I might be looking at, and then I could use matrix or mount method to convert those to forces. And then I would have things like FRFs to the target locations. So I have all this data. And what I'm going to do with transfer path analysis is create a model where I multiply these things together, do things like matrix inversion, et cetera. In the first page here, they have a definition. And the definition is where you define all these paths. And typically you do that by, bringing in the data IDs here, and I can say, okay, I'm going to target, this is the operator receiver location. I'm going to target sound pressure at the operator ear as my target. And then here I have the paths. This is where the source and the structure are, I made the cut and separated it. There's 15 paths here. 3 directions for each path. So there's 5 physical attachments between my structure and my source. And then I have things like the operational force conditions. In this case, it's third order. I might also define, like if I had mounts, which active and passive side measurements correspond to each other. And then I read, and I can see where all the data is. And in this case, I have the FRFs to the target locations. There's 15 of them. And you might be looking at this thinking, this body 1Z looks pretty big. Looks like the structure is very sensitive at this frequency, so that might be the problem. But again, hopefully you remember from the slides before, this may or may not be the case that this will be the problem path. It depends also on the forces that are coming in. And that's what this part here is. Here we select our forces. I had to measure accelerations to indirectly determine the forces. So I don't know exactly what the force will be, but I have the data to do that, and I'll do that in a second. And maybe to point out here, here's the path data where, it's force. Indicators means I'm going to determine the force indirectly. So indicator, indirect. And this is where we have accelerations, because we're going to use them to determine the forces. In TPA loads here, you can go in and you can calculate the forces through mount method or through the, if you have directly measured forces, you get them here. You got matrix inversion for FRFs. And again, it will show you things like the condition number of the matrix, if you have that. After you calculate the forces and you do everything, then you can look at the results. And the results, might look something like this. At this third order, I can see all these different paths. These bars are the results of the multiplication, the force times the FRF. So it's not one or the other, it's both combined together. And in fact, body 1Z ends up being the problem path, because we have the total of all our paths, the measured total, and then we can see that this one lights up. And we can break that down. There's this path-specific display. If I look at something like body 1X, here's the calculated and measured total. They match pretty well. This is the contribution of body 1X in blue here. You can see it's way below the calculated total. How we got this total, we took the FRF times the force here to get the calculated total. And we have active and passive vibration across the mount and mount rate and all this good stuff here. So this is body 1X. Didn't contribute very much according to this chart, right? Body 1X was relatively small. In fact, we can even use a double cursor here and we can say we'd like to understand just for a limited range of this model where we have like one particular peak, what the biggest contributor is. And body 1X is way down there. So it's small. If I look at body 1Z, it's a lot bigger. And let me maybe just make these limits fixed here. If I go back to body 1X, notice, because I set this to a fixed, not auto scaling, body 1X forces are very low. Body 1Z forces are very big. There's that FRF, which is also got a peak. So we had an unfortunate situation here where the forces coming out of the source at high levels at the same point where the structure is very sensitive to inputs. And you can see that its calculated total is very close to the measured total. So there's where our problem is. If you're in an organization where you have a propulsion group and a structures group, you'll get to blame both people, the structures people and the propulsion or power source people for high levels of noise or vibration. Exciting, if I hit edit here, I can do some predictive work. I could say, okay, if I could remove this peak, and maybe it's something a little bit unrealistic, 90% reduced. Then again, if you do a good job with modal, et cetera, it'll now tell you what the new calculated total is, how much you'll reduce the total at the operator ear. And you can do the same thing with any of these things. You can change the mount rates, and maybe you have a few different mount rates you could pick from. You can change the forces, and get an idea of what it would take to get these vibration or sound down to an acceptable level. So I hope that made sense. Okay. Q is acoustic force. And just to explain this a little bit, like if we have like structural FRF, we have force as the input, the output is acceleration. We have an acoustic FRF, the output is sound pressure, but the force for an acoustic path would be Q. And what Q is it's simply the, let's say you had a speaker like this. We mentioned earlier that this Q is meter cubed per second squared. It's actually an area, which is meter squared, times an acceleration, which is an area over meters per second squared. And if you just took an acceleration measurement, multiplied it by its corresponding area, you got meter squared times meter per second squared, and you get this Q value. And so that's how you, one way to quantify Q. Okay. Let me jump up a slide or two here and just give another idea of how Q works. Actually, so you can use the things like a sound source that's calibrated to Q in order to determine FRFs. So you'd have pressure over Q, etc. Okay. I'm going to talk about another concept here, something called blocked forces. People want to take forces that they've experimentally determined and maybe apply them to a simulation model of a new vehicle structure or whatever it would happen to be. But when you measure the forces here, you might be doing it in a test cell or with a vehicle, and instead of being perfectly rigid to get the force, the structure that's holding the mounts has some compliance. And when we go to determine the force, we're looking across the displacement X1 only, typically, but there's some displacement or give in the supporting structure. And if that give is, if there's a lot of give in it, so to speak, it can mess up your force estimate. So if you have a strongly coupled system that interacts a lot, the force estimate would be not off for like troubleshooting or understanding what's going on, but off as far as what we would call a blocked force, which is a force that's independent of the supporting structure. And so, but really, if we want to do forward predictive work, we need what's called a blocked force, not just a contact force that you get, which has the compliance of the test rig in it. And so a lot of people will build rigs like this that they try and make very stiff and try and determine the force from like this rotating tire, for example, which works, at low frequencies where there's very little modes. But nowadays with electrification and everything going on, people have to go to much higher frequencies. Electric motors produce higher frequencies than combustion engines. And the odds are that you'll run into, even on something that looks very stiff like this, at high frequencies, it'll act like a spring and be very compliant and kind of mess up the force estimate. So a blocked force, what we're trying to do is quantify things independent of the supporting structure. And so this is how you calculate a block force. You have to put some sort of infinitely rigid, infinite mass here, when you go to test your source system in order to come up with this blocked force. Okay. In the transfer path software, there's things to support. Actually, like if you had to test with some kind of supporting structure, you can measure FRFs across it to block out the influence of the support rig to get this blocked force. Reason I mention it is this is, you know, a lot of people are trying to do predictive work, and they're trying to make it simple for people to evaluate different structures, use forces that are independent of the you know, are independent so that they can get good predictions, you know, for these you know, trying out different scenarios. And in the test lab software, complementary to the transfer path, there's this virtual prototype assembly, which relies on blocked forces in order to work. With this, you can create different components. So for example, here I selected some FRFs, you know, of my structure, and I can save that as an assembly. And then same thing, you know, I can create a source that's a set of loads that should be based on blocked forces, and create a component like that. And what this lets you do, I'll play a quick movie here to save some time, is you basically can create a library of different parts of the structure. So like in this case, I loaded in a set of FRFs for the receiving structure. And now I can grab things like load components, like different sources, and I can bring those in and assemble a model. So you saw me create the definition of these models a second ago. Now I'm bringing in the loads. I would then end up connecting these. So there's a auto connect here. And so if you make a good library, in fact, when I made these connections, it's deceiving, but a second ago you saw I had a matrix of FRFs. Behind the scenes of these components already set up are all these FRFs. So even though you see one connection here, there is really multiple connections that have been made, you know, because there could be 4 or 5 attachments between the source and the structures. And you can assemble very complicated structures this way. And the idea of, let me go back here a second. So we might have multiple components, some bodies with like trim, some without or whatever. I can create these different assemblies just by right-clicking, picking the different components, connect them all up, and then I can quickly see the results of assembly 1 versus assembly 2. And if I use block force methodology, I'm able to do that and do a really good job predicting things up front. Okay. So I hope in this case, I think we have something with trim and something without. Looks like it's a good idea to have trim. Here, I guess actually I'll replace this component with yet another component. So this one has no trim. Trim meaning like damping material or something on those. It makes those FRFs less peaky. So, and again, a non-expert, if these components are set up correctly, a non-expert can try several different components out, you know, different structural assemblies, and evaluate the effectiveness of each one. So let's see if no trim is a good idea or a bad idea. I think it's looking like a bad idea because the levels are a lot higher. Maybe one other small thing to point out here. Just give me a second. So under this preferences, you know, you see a vehicle body here, but this technology again is used in all sorts of industries. So, you know, even the icons you can switch out and use different icons that make sense for your application. and you can create these, but Simcenter also has its own library of icons. So for example, just give me a second there. We got aircraft, different types of connectors, motorcycles, submarines, washing machines, all sorts of good stuff that you can use here as your receiver location. So, if you're trying to make your sub very stealthy, you don't want all the different pumps that are running inside it to generate noise on the hull. You can use a appropriate icon for that. I kind of glossed over that a little bit, but if you were to go and go on Google and you look for like blocked forces, Siemens, for example, then there's nice articles and movies and things that explain the concept of blocked forces in further detail. This is all on our Siemens community, and you can find out a lot more information there. All right, I think I'm done. Matt, did you want to bring up a Q&A slide?
Yeah, we can certainly do that. Nice job, Pete. Thank you very much. So for folks, for the last 5-10 minutes here, if there are questions, I didn't see any specific in the chat or the Q&A, but those that are on, if you have questions and you'd like to ask those to Pete, we can unmute you and you can speak directly with Pete here on our webinar.
And we did just have one come in on the chat, so I think they beat you, Matt. So
awesome.
Quick question for you guys, just from the chat, is how are the transfer functions determined? Are they test-based or somehow solved via coupled vibroacoustic 3D simulation? Or Pete, could you speak to that a little more?
Yeah, both. They can come from any source. So simulation or test, boundary element or a finite element model. And so that's why that software is called virtual prototype assembly, because you can use, the forces could come from simulation or test, and the FRFs could come from simulation or test. So you could have an all simulation model. You could think of that virtual prototype assembly as a post processor for a big simulation you might have done where you had forces and the structural components modeled, or it could all be test-based or a combination. We used to call it hybrid modeling, and then where you had test and simulation mixed together, but now hybrid means something else, with gas and electric. So hopefully that answered Z's question there. The follow-up question was, are they available in the database? And the answer is no. So these FRFs and forces, the forcing functions in the FRFs, which we're assembling together, you would determine those for your product. So there's not a database of pre-canned things, because we don't know anything about your product, or we shouldn't, because you're designing something proprietary to your company. So you would have to determine the forces and the FRFs that are in your product. Certainly ATA is willing to do project work to help you determine that if you haven't done that before. You can also, if you actually have a physical product, it doesn't take a high amount of effort to do the measurements, with an impact hammer or other. So hopefully that answered your question. The library, maybe I should explain, the library I was showing earlier would mean usually there would be maybe more of a noise and vibration expert in the company who would make sure that these components are valid. And he would publish those components so that any design engineer colleagues who aren't noise and vibration experts could do these different combinations. It would tell them if it fits together, does it have the right amount of mounts and everything. But that noise and vibration expert would determine those components beforehand and make it easier for other colleagues in the organization to assess noise and vibration performance. So hopefully that makes sense.
think so, Pete. That's fantastic. We have a few more minutes, folks. If there are other questions, we can certainly address those with Pete on the call. If there aren't, we can definitely follow up with myself and Pete after the call. And again, we'll publish the recording and we'll share that when it's available. I'm not seeing more questions, Jonathan. We can give another couple seconds here. If there are, please raise a hand or type them in. If not, Pete, that was a wonderful job. Thank you very much for your time today presenting. Folks, thank you for joining us. We appreciate your interest in transfer path analysis and ATA and Siemens. We're here to support you. Again, please feel free to reach out to us at www.ata-e.com. This is Matt Schumann and Pete Sheldonbrand. On behalf of all of us, thank you for joining us. Have a wonderful afternoon.